All right, we can start 110.
So the tours at Microchip looks like we're going to fast. So honestly, I have no idea what we're doing. I don't even know what to do. So we'll just get what we get. It's super fun if we can go into the fast. But hopefully you saw the rules. There are a few rules like no cologne or perfume. I don't know how they're gonna test that. They're gonna smell us. From what I remember, they didn't do any of that stuff. So, but anyway, try to meet all these, like look over it a little bit. And then these, of course, are important when we're in the fab. So you don't like take off your bunny suit. The only time I've had a problem with this is we did have a student that was claustrophobic that thought this was still a good idea. And they freaked out how they do it. You can't leave the tour once you're in the tour. So that's the problem. And so,
so it says on there that you can't use a cell phone anywhere in there. You have it on.
I think you can have it on, you just can't pull it out. Yeah. So I do remember this, people were coding. So don't like wear your thermal long johns and your hoodie and your coat in there and then put all that under the bunny suit. That's bad. So I'll probably walk in with just a t-shirt, but we pulled from my card at Microchip, and then maybe we'll be overheated within this. So there you go. And if you're claustrophobic at all, then this is probably a bad decision. So yeah, just communicate with me, right? Any other questions on that? Yeah, if when they talk about the equipment, really zoom in on what they're trying to tell you. I've been through this tour a number of times and some of this equipment is unbelievable. So it's pretty interesting to walk through it. All right. Any questions about anything else before I start my stuff? Pretty sure I opened that. All right. The good news and the bad news, I guess. I'm caught up with my grading, and if I had to give grades right now, this would be the distribution. Which is great. Like there's 40 of this. So if you're not checking your grades, you need to be checking your grades. Seeing where the zeros are and addressing them. So a little fear factor here. Check it out. All right. I don't really like downers like that. This is really a class where you just got to get everything done, right? It's not super difficult. You do got to keep track of it all and get it all done. All right, last time we talked about equilibrium, we talked about tensile stress. That's pretty straightforward. Usually engineering students can get the whole load over area and compare it to some properties of materials. So a couple of games have sent me some stuff on calculations. They look pretty good so far. The big thing I'm going to look for is that you isolate one little part of your system to do this analysis. And I'll need to know what part that is. So you should be able to maybe find something that's like the one example I gave you class that's in tensile stress, right? So the important thing is that you calculate that stress and then you compare this like on paper, right? The only reason we ever do a stress is to look at that stress and compare it to some actual properties of material. You should be able to look up any kind of material online. It can get complicated. It can be in the metric system in the US system. You're looking for PSI, pounds per inch squared. It's typically the unit that's recommended. Okay. So we should be able to get one of these, and you should be able to get a bending stress also in your product. And again, I'm here to help with that kind of thing because you've not had these classes. So if you look at your project and go, man, I just don't know what to do as far as the calculations go. Yeah, oh, you just do this piece and we'll simplify it, right? We're not going to do the full analysis. So I want to go through bending stress.
And then I want to leave you enough time to travel to the field trip, so we'll be done a little bit early today. All right, so bending stress is this equation, MC over I. So this is a very big design equation. We typically design in bending and we check all the other stuff. So after we design whatever we're designing in bending stress, and we choose the size of our piece and the material, and we make sure the bending stresses are good, then we go back and we check all the other stresses, like a tensile stress, or a shear stress, or a torsion stress, or the deflection, all the other things we do when we're doing this, right? But bending stress is kind of our control, because usually it's the thing that fails first. Fails in bending, long before it typically fails in tensile or shear. So if we can get a little bit of a handle on this bending stress thing, that would be good. So I'm just going to go through the pieces, M, C, and I. M is the hardest one because M is the load. It's called a moment. You can think of it as a torque. So if you know what a torque is, now you know what a moment is. So it's the same thing. You take a wrench and you twist the bolt, right? And let's say most of us understand that example, so that's why I'm using that one. So here's my bolt head. And then your wrench comes off of here, right? Wrench. And we're going to apply a load. How much load can we apply on a wrench? Let's say it's a 12-inch wrench, kind of big wrench. Right? 12 inches, about this far. How much can we push on it?
Entire body weight?
You're a better mechanic than I am. Usually I'm laying on my back and I'm pulling on this wrench and I can barely get a load on it. Entire body weight. That's standing on. You're gonna break it.
There's also the dynamic weight of when you're throwing down.
All right, we don't need to get into dynamics. Let's keep it simple. Just give me a load. How much can we push on this thing?
150 pounds.
150 pounds. Holy crap. I'm telling you, I can't get 150 pounds on my wrench. Okay, so it's a torque. Moment is torque. So how much does this rotation, and I'm going to use an arrow to demonstrate torque. Can you see that? Not really. You got to say something. Is that better? I know it's got its own shadow. Can you see that better? The rotation? Yeah. No, I'm not moving it. I can zoom it. Is that what you mean? Still has a funky shadow. There, is that better? Yeah. All right. So we're 12 inches out to this 150-pound force. Right? Everyone understand this little drawing? Yeah. So what we want to know is the torque here, and engineers call it moment in some courses, and we call it torque in other courses. So in statics and strength of materials and force analysis, we call it moment. And the moment equals force times distance. So that's force, that's distance. Now the force has to be perpendicular to the distance. Perpendicular means at right angle or 90 degrees. That means that the line of action of the force and the distance have to make 90 degrees. That's what perpendicular means. Yeah? So then the equation for moment is force times distance, as long as that distance is perpendicular to the force. And I designed it that way, so our force is perpendicular. Or most of the time, when you're pulling on a wrench, sometimes you can get it perpendicular, a lot of times you can't, right? So that just decreases your moment, but we won't go there. We'll just keep it simple like this. So our moment's equal to what?
Pounds.
Yep, 150 pounds times 12 inches. It's not gonna be foot pounds, it's gonna be inch pounds, yep, and it's 150 times 12. What's that number? I should hear calculators opening up and turning on, yep. 1,800. Inch pounds, 1,800 inch pounds. That's a moment. Okay. So that means at that location, and moments are specific about a location. They're not just like anywhere, they're specific about a location. Right? Because we have to do force times distance, and distance is due at a very specific cost. So that's important. So that's what a moment is. Now, when you apply it to a beam, which is what I'm thinking you'll be able to do in your project, the beam sets up a little differently. And I had this on screen before. And I don't remember how much load we put on it, like 400 pounds or something. 400 pounds, and then we just said, hey, how much is here and here? 200 and 200, so that's the whole equal and opposite force, right? We have 400 coming down, we need 400 going up. All right, so now, this moment thing, what's this beam feeling? It's feeling two supports here, right? And if I have my assistant push down, don't break it, okay? Push down, what happens? It bends. So what's happening is these ends are doing, what are the ends doing? They're rotating, actually, they're pushing up, but if they're free, which if I hold it like this, that's what we call a free end. I'm not grabbing it and holding it, right? I'm not encasing it in concrete. I'm just putting the support underneath and underneath, push down again. Those ends are free to rotate. That's good. That means it's free to bend, and we want things to bend, right? But that rotation, those are called end rotations, and those are moments. So this material or that material can resist internal moments. Remember, moment is a torque. So this thing can resist internal twisting. That's what that bending stress is. The load is this internal torque. Well, how do we calculate that? It's definitely a much harder problem, but I'll give you the easy version. Where do you think the maximum stress occurs when we load this 400 pounds in the center of our beam? Right at the center. Yep, good guess. So that means right here is where the maximum moment occurs. Now, this is only one load condition. So welcome to engineering. If you were going to analyze this beam, you have to consider every load condition. Good luck with that. That includes 777 flying into the right? A load condition that was not there when that happened. All right. So we want to know M right here. What was M again? What was the equation? Force times distance. Trick question. How far is it from the 400 to that center point? 0. So the 400 is creating no rotational effect about that center point. Does that make sense? Kind of weird, but that's true. How far is it for the 200 to the center point? Yeah, we'd have to know how big it is. We'll say it's 3 feet. So the overall is 3 feet, so this is 18 inches. Right? So the internal, this is internal to the structure inside this thing. That internal moment is force times distance. So we look for the force that is furthest away, and it's the 300 pounds. So when you do that, what you're essentially doing is you're cutting this beam in half. You're actually getting rid of one half and then understanding what goes on right here. What goes on right here is 200 times 18. It's not 200 times 18 plus another 200 times 18 because these are fighting each other. They don't add together. So it's just one of them times the 18. So the moment here equals 200 pounds, 18 inches. What's that number? How much? 3600. And the units? Inch pounds. So we'll say that's our load on this. How do you think that's going to work? 400 pounds in the center of this. How much do you weigh? We need a few of you, right, to get our 400 split in. Okay. So that's what we're going to say. This is what we're doing our analysis, right? 400 pounds in the center of this. We're going to try and determine if this is going to work or not. We have a feeling it's going to work or not, right? What do you think?
No.
No, thanks. All right. So that's our moment, our equation. MC over I has two more pieces. The M is this. It's essentially the load. That's M. Okay. Good so far? What is C? C is the distance to outermost fiber of the cross section. What is a cross section? Huh? Oh yeah, that would help, huh? Guess that doesn't work. It is, but what is a cross section? If I said this is my beam, what's the cross section of this beam?
The width and the depth.
Yeah, it's that. It's the end view of your. That's the cross section. Okay, this is my beam. Here's my 400 pounds. Here's the two supports. What's the cross section? The cross section is where we did that moment. How much material is there and what's it look like? Okay, so this is the cross section. This rectangle is the cross section. If you had an I-beam, shape of an I, that looks like an H. The cross section is an H. If you had a 2x4, the cross section of a 2x4 is right here. It's that rectangle, which is not 2x4. Yeah, it's inch and a half by, yeah, 2.5. All right. So C is the and the reason is when he loads this, but when he loads this, what's happening to these fibers? The top fibers compressing. What's happening to the bottom fibers here? Stretching, right? So what's happening stress-wise on that cross-section? Those outer fibers is what cares about. The ones in the middle actually don't even know what's going on. In the direct middle, they don't feel anything. But when I do this, these top fibers are compressing, not going to hurt anything, but the bottom fibers are trying to literally shred, right? Tensile apart. All right. So the position of your beam is important, whether it's like this or like this. I'll explain that in a second, but I'm doing it like this, right? So that means this is my cross section. And just for ease, that's about 1.5 inches. It's not 2 inches. All right, we'll say 1.5 inches. 1.5 inches. And then this will say, it's probably not a quarter, but we'll say it's a 1/4 inch, 0.25 inches. That's my cross section. It's this. right? Because I'm loading it like this. I'm not loading it like this. Should be, because it's way for heck strong that way. This way, nothing. All right, so C, every shape has a geometric center, and C is the distance from the outermost fiber, the geometric center. From the center to the outermost fiber is C. So what is our C value? 0.25 divided by 2. 0.125 inches. So whatever shape you have, if you have a pipe, right, if you have a PVC pipe, that's a round shape. Where's the geometric center? Right in the center. It's not a trick question. Yeah, this is about the easiest shape. It's almost as easy as a rectangle. Where's the geometric center? It's like in the center, halfway up, halfway up, right? Height? No, it's in the center. So there's some very simple shapes. Rectangle in the center, right? That's where geometric center. Now it gets more complicated, like a C shape. Where's the geometric center? It's like a little over, a little up, right? So there are shapes where we have to look them up. And then, of course, we do a lot of composite shapes, and you have composite shapes, you have a bigger problem. So keep it simple. Keep your cross section simple that you're going to do your analysis on. Okay. Questions about this? What C is? So for different shapes, different cross sections, like if it's an I shape, that's pretty simple because it's symmetrical. Just got to know how tall it is, and it's just half of it, right? Same with a rectangle or a square. Geometric center is pretty easy to find. Okay, keep it simple. Pipe, easy to come up with C values. All right, the last thing we need to know. Inertia. And now this is not your inertia from physics class. Inertia from physics class is like big heavy object moving through space, right? How much inertia is that? That's a dynamic inertia. This is called area moment. This has to do with an area. Again, our cross section is what this is. So different cross sections behave differently under load. This cross section behaves differently under load. If I hold it this way and load it straight down, it's very flexible. You just won't carry load. If I hold it this way and try to do the same thing, I literally cannot move. It's stronger than I am this way, and I can just bust it in half, no problems. So the position of your cross section compared to your load is critical. And area moment of inertia gives you that number that says, oh, if the inertia is high, you will have a lot of resistance to bending. If the inertia is low, you will have like no resistance to bending. Regardless of the material doesn't matter. We made it fluid, silicone, or steel, or technique. Doesn't matter because it's all about the cross section and the position. So let me just show you an example of that. And again, every area is going to have its own inertia equation. A pipe, look it up. It'll have an inertia equation. A rectangle, look it up. C shape, look it up. L shape, I shape, they all have their own inertia equation. A rectangle is the simplest. Base height cubed over 12 for I of a rectangle. Base height cubed over 12 for I of a rectangle, inertia of a rectangle. Okay.
And really, remember, inertia is just this number that helps us with its ability to bend. Like, hey, I wasn't shaped in a bend.
So let's apply it to this. Base is the base, that's 1.5 inches. Everyone see where I'm getting that number? The base is from here to here, 1.5 inches. What's the height? 0.25 inches, and we do what with it? We cube it, and it's over 12. That's the inertia of this in this position. That's a pretty low number. We calculated for me. Anybody got it? Or are you just not trusting your calculator? How many zeros? 0.0019. That's what I get. Yep, that's about as small as you get. And I'm gonna make my rectangle like this, because that's the position. 0.0019. What's the unit?
That would be 1,009 of a thousand.
True, let's just go with 0.0019.
Actually, I would run.
That's good. But what's the units? Inches to the third times inches,
Ah.
inches to the fourth.
Yeah.
Super cool. If you look that up or you read about it, they'll say it's just the mathematical quantity. Don't get all bent out of shape about inches to the fourth. Seriously, it is just the mathematic quantity. So inches to the fourth, that is its unit. And when you look up inertia, it'll be inches to the fourth. Okay. Super small number. What if it was in this position? So that means your resistance to bending is almost nothing. And that's true. What would it be if it was this way? What's our inertia? If it was loaded this way. So notice my symbol's going to change. And now I'm going to have a tall rectangle. What's the base? So it's in this position now. And this is called the strong position. So the base is 0.25 inches. The height is 1.5 inches cubed over 12. It's the same equation. It's still a rectangle. It's just in a new position, right? What's that number?
0.07 inch.
Anybody else get that? Yep, nope. Yep. Yep. Much bigger. They're all really small numbers because guess what? This is not very good structural material right here. We don't build many things out of this, right? But it's much better, much better. Now you have the pieces. You have M, you have C, and you have I. And let's do I in this weak position. This is the I that we want to use because that's where we started it. I just did this so you could see the difference. But calculate me a bending stress now. So the whole equation now is going to be bending stress equals M. What was our moment? 36,000.
3,600.
Oh, 3,600, thank you, inch pounds. And what was our C value? 0.125 inches. And now we have an inertia of 0.0019 inches to the fourth. And if you do the unit analysis on that, you have inches squared above, you have inches to the fourth below. That leaves us pounds per inch cubed.
inches squared below. Right? Yep. Yeah. And pounds above. So pounds per inch squared, PSI, which is what we want. Calculate that for me.
225,000. 225,000.
Anybody else confirm that? Anybody else got that number? Oh, we have a disagreement. I get. Wow, I get a big number. How big of a number did you get? Yeah, I got way bigger than that. Oh, that's where I went wrong. Yeah, 236,000. Rounded up 237,000. 237 PSI. Right? I rounded it up. Anyone remember what I said the bending allowable stress was for wood or Doug fir?
900 PSI. What do you think our 400 pounds is gonna do to this thing? Yeah, it's done. It was done a long time ago, we just finished it up. That's it, that's why you got this. Oh, the giant bending stress. This will never carry that. All right, that's your rundown on the two stresses you can do in your projects. Let me know if you need help. We're gonna stop here, give you enough time to get to microchip. Anyone know the drive time to microchip? It's like 6 minutes or 7 minutes. So. Go right. You'll be fine. See you in the lobby about 2:20. Tour starts at about 2:30.
But people out there stay alive.
Right?
Same thing.